Everyone, Dr. Ross back with Chapter 3 lecture from this introductory chemistry course, or Chem 65 as it's known. In this class, we're looking at atoms, molecules, and ions. And the contents of this lecture will be atomic theory, molecules and some nomenclature, which is just naming chemicals. We'll look at formula masses, and we'll look at ions and ionic compounds. So without further ado, let's begin. Okay, atomic theory. So it all started in the early parts of the 19th century with John Dalton, who was an English naturalist. And based on the known laws of matter at the time, which we'll actually look at in the next slide, he proposed Dalton's atomic theory, which has some postulates that I would recommend that you memorize. Not all of these postulates are correct by today's standards, but at the time they were groundbreaking. So he theorized that atoms are the smallest indivisible particles of matter, still retaining a chemical identity. So for example, if you have an iron bar, what's a piece of iron? Well, if you grind the iron bar down, and if you hypothetically imagine you can't grind it down anymore, you've got the smallest possible piece of iron, that's an atom. That's what he theorized. And if you build that building block up, you can generate any size piece of iron that you like. And every piece is the same as every other piece. He then theorized that all atoms of an element are identical. We know that that's no longer true today because we are aware of isotopes, which are flavors of elements, but Dalton didn't know that at the time. Postulate 3, atoms of different elements are chemically different. That's true. So for example, helium is identical to every other helium, or every flavor. There are flavors of helium, but within each flavor, they're all identical. An analogy would be if you take the yellow Skittles, then if they were like atoms, all yellow Skittles would be identical, but they might be different than red Skittles, for example. So that's certainly true. And they're all, helium is different than hydrogen, hydrogen's different than oxygen, oxygen's different than carbon. And we'll see why later in the course. Postulate 4, atoms can combine in whole number integer ratios to form compounds. True, they can. Chemical reactions involve rearrangement of atoms, not a change in the atoms themselves. That's true. So that was his atomic theory. And his atomic theory built on the shoulders of these laws. So conservation of mass law was theorized and proposed actually based on experiment by Antoine Lavoisier towards the end of the 18th century. And it essentially posits that mass can neither be created nor destroyed, but you can convert it between forms. Law of constant composition, proposed by Joseph Proust, again towards the end of the 18th century. That basically says that compounds are made of whole number integer ratios of building blocks or elements. So for example, water is made from 2 hydrogens and 1 oxygen in a 2-to-1 ratio. Always. If it's in a different ratio, it's not water anymore. And then multiple proportions, you can have different molecules made from different ratios of the same stuff. This was proposed by John Dalton. So for example, if you take nitrogen and oxygen, you can combine them in a 2-to-1 ratio, a 1-to-1 ratio, a 1-to-2 ratio, a 2-to-5 ratio, and there are other ratios. These are exact, but they're all different. So it's a multiple of exact ratios. It's a multiple of proportions. I would recommend that you know these 3 laws of matter. Nomenclature, this essentially is naming chemicals. We are going to follow the IUPAC system, which is an acronym for International Union of Pure and Applied Chemists. So essentially, there's different types of naming conventions. Type 1 ionic compounds are ionic compounds where the metal ion can only form one type of charge. So there's no need to specify what charge it is. It's always the same type of charge. Type 2 ionic compounds are when the metal can form a multiple variety of charges, so you must specify what the charge is. You can't assume what it is because it can have a choice of charges. Covalent compounds are not ionic. We'll see how to name them. They follow a different procedure. And then finally, we'll look at acids and bases. Oh, actually, I think we'll just look at acids. But I believe we'll just look at acids here, yes. Okay, so for example, sodium sulfate, we know that sodium is an alkali metal. It's a group 1 metal. It can only possibly form one charge, and that's a positive 1 charge. So there's no need to refer to the +1 charge in the name. It's sodium. It can only form a +1 charge. Sulfate forms a -2 charge. In a couple of slides' time, I'll tell you that you just have to memorize the charges of polyatomic ions. Sulfate is an example of a polyatomic ion. It's an ion made of many atoms with a charge spread over the whole thing. So you eventually, and eventually means very quickly, will learn that sulfate has a -2 charge. And if sodium has a +1 charge, you know that you need 2 sodiums to offset the -2 charge on sulfate. So we have a Joseph-Proust definite proportion of 2:1 between sodium and sulfate. Zinc chloride, zinc is unusual. It's a D-block metal, but it can only possibly form one type of charge. That's a +2 charge. Chloride forms a -1 charge only. So if you've got a +2, that's why you need 2 -1 chlorides in a Joseph-Proust definite proportion of 1:2 between zinc and chloride. No need to mention the charge on the metal here. Conversely, type 2 ionic compounds, you do have to mention the charge on the metal, and you do so by Roman numerals here, which are known also as stock notation. So iron 3 sulfide, the Roman numeral 3 tells us that this is an ion with a +3 charge. Sulfide has a fixed -2 charge on it, and there are 3 of them, so that's -6 total charge. If I've got 2 iron 3s, 2 3s are 6, the +6 from the iron, the -6 from the 3 sulfides sum to 0. The sum of all charges in an ionic compound must always be 0. So because iron can form different charges, I specify in this particular compound, it's a +3 charge. And from this information, I can deduce the 2:3 definite proportion between iron and sulfide. Similarly, nitrate, you will quickly learn, has a -1 charge. Here I have 2 of them. I put nitrate in parentheses because I want the multiple 2 to apply to the entire structure nitrate. So I have 2 nitrates. So I've got 2 multiples of -1 charge for a total of -2 charges. 1 lead, the lead must therefore have a +2 charge. So I know it's lead Roman numeral 2. Covalent compounds don't have charges, they use prefixes. So for example, dinitrogen tetroxide is 2 nitrogens and 4 oxygens in a 2:4 Joseph-Proust definite proportion. Sulfur hexafluoride is a mixture of 1 sulfur and 6 fluorides in a 1:6 Joseph-Proust definite proportion. So there are prefixes that you would have to learn. They'll be provided in a table in your textbook. But briefly here, mono is 1, di is 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, nona is 9, and deca is 10. Okay. Okay, molecules and nomenclature. Acids, there are two broad types of acids that we'll see in this course. There's binary acids and oxyacids. Binary acids, for example, are a combination of two elements. The first one is hydrogen, the second one is something else. So you take the ide of the anion. So here, HCl, we can see it's chloride, and then we add the prefix hydro and make the ide, change the ide suffix into ic acid. So for example, HCl would be hydrochloric acid. The second example here, HOCl. OCl minus is the hypochlorite ion. So we've got hypochlorite ion. This would be called hypochlorous acid. We've got HNO2. This is a weak acid. The NO2, the nitrite ion. This just becomes nitrous acid. This is an oxyacid. Another oxyacid, we've got bromate. A bromate ion becomes bromic acid. And finally, in this example, we've got perchlorate ion. The ClO4 minus ion is perchlorate ion. This would form perchloric acid. By far the best way to learn names is to look at a list of names, and just you will naturally acquire how to name them. So it's almost counterintuitive. Looking at a list of rules, very quickly your brain will see a pattern. So I'll be providing a list of no names in the lecture. Okay, this is a flowchart that you can follow. Again, early on, you can start to follow the flowchart to derive the name, but eventually, pretty quickly as well, your brain will start to siphon through these flowcharts in a natural way to name chemicals. Formula mass, this is the mass of whatever formula you're looking at. If the formula is an atom, it's the atomic mass. If the formula is a molecule, it's the molar mass, or the mass of that molecule. So for example, if we want the mass of anything, we take the atomic mass given to us, we take the atomic mass unit away, we replace it with gram, and by definition, that's the mass of a mole of that material. So in this first example, we have copper 2 phosphate. The structure is shown. We have 3 coppers. So we have 3 moles of copper. We look at the periodic table. The atomic mass of a copper atom is 63.546 grams. By definition, we set that equal to a mole. We have 2 phosphorus atoms. The atomic mass of phosphorus from the periodic table is 30.973761. We set that equal to a mole because by definition it is a mole. And then we have 8 moles of oxygen because the 2 and the 4 here multiply. And the mass of one oxygen atom from the periodic table is 15.9994 grams. We add these all up. We are limited by 3 decimals because we're adding 3 decimals to 6 decimals to 4 decimals. So we're limited by 3 decimals. That's why you've got the dashed line after the 3rd decimal. And this would be the mass of the entire structure. So if you want 1 mole of copper 2 phosphate, you have to go way out, 380.58072 grams. Ions and ionic compounds. So you can, again, part of the naming is to know based on location what the charge is. So nonmetals, type 1 nonmetals, typically have a known charge. So for example, halides are always -1 charge. Things like oxygen and sulfur are always -2. Ions like nitrogen, or sorry, oxide, the oxygen element becomes oxide when it's ionic. Oxide and sulfide have known -2 charges. Nitride and phosphide have known -3 charges. You know them, you can predict them, you don't have to specify the charge. Type 1 metals like alkali metals have a fixed +1 charge. Alkaline earth metals have a fixed +2 charge. Then there are other types of special elements that have fixed charges. These are the 4 other types of elements that have a fixed charge. And then if we have those elements in combination with something that's less familiar, based on the ratio, we can calculate what the missing charges should be. In terms of polyatomic ions, so sorry, you just have to memorize them. This is a non-exhaustive list of some common polyatomic ions. So for example, we have carbonate. The formula is CO3 2-. So it's a carbon, 3 oxygens, all connected together, and the whole thing has a -2 charge spread over it. So that's something you'd have to memorize. Nitrate, as another example, is a nitrogen with 3 oxygens, and the whole thing has a -1 charge spread over it. You would just have to memorize that. So it's well worth memorizing a table like this, so that you don't have to look up these types of things. This shows you the difference between type 1 and type 2 ions. So for example, group 1 or type 1 ions are always +1. So you don't have to give stock notation or those Roman numerals for any compounds where the cation is one of these ions. Alkaline earth metals always have +2. You don't have to specify with Roman numerals here. Things like halides always have -1. Don't have to specify those. Things like oxygen and sulfide, oxide and sulfide, -2. Conversely, iron, the ion iron, IRON, so that's a mouthful, can have a multiple of charges, so you do have to specify the charge on those. It can be +2 in some compounds, it can be +3 in other compounds. So you would have to specify that with stock notation. When you write formulas, the formula is valid if the sum, well, one way that you know the formula is valid is if the sum of all the ions is, the sum of the charges of all the ions is 0. So for example, lithium always forms a +1 charge in its ionic form. Fluoride always forms a -1 charge in its ionic form. A single positive charge and a single negative charge can come together in a 1-to-1 Joseph-Proust definite proportion to form a neutral ionic compound. So lithium fluoride in a 1-to-1 ratio of lithium and fluoride ions is a valid ionic compound. However, if you take something like barium, which is an alkaline earth metal in group 2, it always has a +2 charge. And then phosphide, which is in group 13, 14, 15, so it has a -3 charge. You can see that these can't come together in a 1-to-1 ratio because a +2 and a -3 won't sum to 0. But a +2 and a -3 do factor into 6th. To get to that common factor, you have to scale the +2 by 3. So you have 3 lots of barium. You have to scale the -3 by 2 to get -6. And so to get a plus and a -6, which would sum to 0, you have barium and phosphide in a 3-to-2 Joseph-Proust definite proportion. And that will conclude this video.